Okay, so 9-7, day 2, Taylor's theorem and the Lagrange remainder. So pause the video, work on this for me, find a third-degree polynomial given this information. The value of the function is -1, the derivative of the function at 0 is 5, the second derivative at 0, and the third derivative's value. Okay, so if we think about approximating, all right, these polynomials we're creating are used to approximate functions, then we have to consider the error associated with our approximations. So the actual error in an approximation versus the error bound, we'll get into that. If f of x represents the exact value of the function, p sub n is our polynomial approximation, then we can use this thought of what a remainder is. Okay, so the error associated with the approximation is the value of this remainder. And notice that it's the absolute value. So the error would be the absolute value of the actual function minus the approximation that we found from the given polynomial. Okay, so given this function, 1 over 1 minus x, approximate f of 0.1 using a second degree Taylor polynomial. Okay, so I'm going to find second degree approximation. Okay, now when I look at 0.1, it doesn't tell me where my center would be, but I'm going to have my center be 0 because that's really close to the value that I'm approximating. So start with our function. F of 0 is equal to 1. The first derivative of the function, so I'll rewrite this as 1 minus x to the -1. So that'd be -1 times 1 minus x to the -2. And the second derivative would be 2 times 1 minus x to the -3. So the first derivative at 0 is -1. Oh, hold on. Forgot my chain rule. Derivative of the inside would be -1. Derivative of the inside here would be -1 as well. Okay, so the derivative at 0 would be +1. And then looking at the second derivative, my first derivative would really be 1 over 1 minus x quantity squared. So then using the derivative, the second derivative, this would have to be -2 quantity 1 minus x to the -3, and then by my chain rule times -1. So the value of the second derivative at 0 would be +2. So my second degree approximation, f of 0 is 1 plus 1 times x plus 2 times x squared all over 2 factorial. So it becomes a nice function, 1 plus x squared. So then to approximate f of 0.1, plugging 0.1 into my second degree polynomial, and you'll get this to be 1.11. So that would be my approximate value. So that approximates f of 0.1. Okay, so in part B, find the error of the approximation. So the error is the absolute value of the function's value minus the polynomial approximation. So my function value, if I'm looking where x is equal to 1/10, okay, 1 over 1 minus 1/10. So my function value would be 10/9. And we'll talk about how to use your calculator completely for this. We'll do that function in class. But we found our polynomial approximation to be 1.11. So subtracting those, I get my error to be 0.001. Okay, so it's a very close approximation of what the actual value of the function is at point 1. All right, find the error for the 4th degree polynomial approximation of the function cosine when x is equal to pi over 4. So again, I'm going to center this at 0. Okay, so f of 0 is positive 1. Cosine of 0 is 1. So now let's go through our derivatives. First derivative, negative sine of x. Second derivative, negative cosine of x. Third derivative, sine of x. And our fourth derivative is positive cosine of x. Okay, so the value of the derivative at 0, these approach 0. So the second derivative would be negative 1, and the fourth derivative at 0 would be back to positive 1. So now when I write my 4th degree, I actually only have 3 terms. F of 0 is 1 minus x squared over 2 factorial, and then plus x to the 4th over 4 factorial. Okay, so don't forget where the coefficient comes from. The coefficient comes from the value of the derivative divided by n factorial. Okay, so again, using our calculator, if I plug pi over 4 in for x, I get, and I'll keep a couple extra decimal places, so verify that you get that in your calculator. If you don't, your mode's wrong. So then the error would be the absolute value of the cosine of pi over 4 minus our approximate value, and that would come out to 0.0003. So a small error in the approximation and the actual value. Okay, so here's Taylor's theorem. Okay, if a function is differentiable through order n plus 1. So notice what this is. Okay, this is our Taylor approximation at x is equal to c. There's our center. So then notice here on the n plus 1 term, that's where our remainder would come from. Okay, so what's the remainder? It would be the n plus 1 derivative at z divided by n plus 1 factorial, and then here, so just in our function, we've replaced our n's with n plus 1. So this is known as the Lagrange form of the remainder, and it represents the error bound, which is the maximum error in the approximation, okay, as opposed to what I said here. What the error would be, okay, the error is the difference in the function and its approximation using one of a Taylor polynomial, but the Lagrange gives us the maximum error for what the approximation could be. And we will practice this in class, okay? Let's talk about this z here. So you're told that z is some value. There exists z between x and c. Okay, so z, what's c? C is our center. And x would be the value that we're actually approximating. So in the previous example, or in the first example, x would have been 0.1, the center was at 0. So what does that mean? Z is going to be some value between those two numbers. Okay, so z cannot be found exactly. It's generally going to be one of these numbers. If that's going to be the maximum, then the maximum is most likely going to occur at one of the endpoints, either the value of x that we're looking to approximate or what the center is. Okay, and we will work on this, but let's just look at how easy this problem is. Find an expression for the remainder of the 4th degree Taylor polynomial approximation of e to the x centered at 1. Okay, so I'm not looking for the error bound. I want to know what an expression for that bound would be. So the remainder of the fourth degree actually has to come from the fifth derivative. Okay? So the remainder of n comes from the n plus 1 derivative. So the remainder would be the fifth derivative at z all over 5 factorial times x minus 1 to the fifth. Okay, this would be an expression for the remainder. Now notice what I do not have. I don't know what x is equal to. We haven't been told to approximate it, so I can't find a value for the maximum error. But going through the steps, I can do as much as I can. So if my function is e to the x, then all of the derivatives of e to the x are e to the x. So the fifth derivative is just going to be e to the x. Oh. And therefore, if I want the fifth derivative at this value z, that's exactly what it's going to be, e to the z. So the remainder of the fourth degree polynomial would be e to the z over 5 factorial. We can write that as 120 if you want, times x minus 1 to the fifth. That's the expression. Okay, and where does z come from? Z is going to be some number between 1 and whatever x is. Okay, so if I wanted to know what the error if x was equal to 1.1, or maybe if x was equal to 0.9. So depending on these, because it can equal those values, z will be one of those two numbers. I'm sorry that keeps changing. Okay, so we'll talk more about this in class, but homework for tonight. Given an expression for the remainder, or give an expression for the remainder of the first degree Maclaurin polynomial for the given function, and then find the maximum error for the cube root of 9 using that first degree polynomial expression at a half.